Okay, good morning. So this is week 7. I'm replacing Dr. Nasra Amri on the topic of refrigeration and heat pump cycles. So today is 20th, so we are on our week 7, and this will be a recap from last week, 17, where I discussed with you a little bit about refrigeration and heat pumps. And so basically this session will be about a work example of how you can analyze or or understand a little bit more about refrigeration and heat pump cycles. But before we dive deep into that, the most important parameters for this section is the COP. So let's have a look at the definition first. So COP is coefficient of performance. So it's basically the inverse of thermal efficiency. Now we have two definitions here that we need to remember, and we will be used often for this section. One is COP R, which is R stands for refrigerator, and COP HP, where HP stands for pump, heat pump. Now, by definition, COPR is for cooling effect of a refrigerator. So by definition, this is definition, remember, cooling effect, the energy from the cooling effect divided by the work input is the definition of COPR. And for the case of heat pump, heat pump is basically a heating device. So you have heating effect divided by the work input. And the definition, if you observe here, it's QL, meaning on the lower end, and QH is on the higher end. So one is for cooling and the other one is for heating. Now if you look at the definition again, you have QH minus QL, which is actually equivalent to the work being used in the cycle. This W net is actually the work input of the cycle. Now if you divide the right hand side and the left hand side with work net and you do the algebra over there, you will end up with the relation of COP for heat pump and COP for refrigerator. Now from this equation, it is obvious that COP for heat pump is larger or equals to 1, because COP for refrigeration is also usually larger or equal to 1. So next thing is another definition. QH minus QL equals work net, W net, and if you divide the left hand side and the right hand side with QH and you do the algebra, and you will come up with the conclusion of COP HP is equivalent to 1 over 1 minus QL over H. So this is the general description for COP heat pump, for the heat pump. Now the reason I'm showing you this is because let's see, it's because in your textbook page 609 there's a definition there, COPR for Carnot and COP heat pump for the Carnot cycle version, which we will look at later. The next one is for COP refrigeration, and if you divide the right hand side with QL, and you will get your final form of COPR, which is 1 over QH divided by QL minus 1. for Carnot cycle, QL divided by QH is just a function of temperature. So you can simplify them in the form of the lowest temperature divided by the lowest temperature, or vice versa, depending on your numerator or denominator. Hence, that's why you get your final equation 11.4 and 11.5 on page 609. So this is page 609. Okay, so this is where how you get that conclusion. So with that in mind, let's move on to our work example. Okay, because obviously it's a lot easier to learn from example rather than to learn from the abstraction. So this is on page 612. Okay, example 11.1. So I've written that down there. It's on page, it's example 11.1. Okay, now the TS diagram still revolves around the saturation line. So the saturation line for a refrigerant is drawn in blue color here. Okay, and the cooling cycle starts from 1 to 2. This is where the compressor compress the coolant, exactly the refrigerant, sorry, not the coolant. Refrigerant is the more exact terms. So this is where the compressor compress the refrigerant from state 1 to state 2. This is still in gas phase. So the process there is isentropic compression. And then the heat from state 2, and bear in mind temperature at state 2, T2, should be larger than the temperature at the environment. Okay, because heat goes from high temperature to low temperature. So the compressor must compress the refrigerant so that it reaches a temperature higher than the environment temperature. And then the heat from the refrigerant is removed, or we have the 2 to 3 process, which is the constant pressure. This is a constant pressure line, and the heat is rejected from the condenser. Okay, this is a constant pressure line, so heat is rejected here. So this is the part where heat rejection is in high temperature. Okay, and then from 3 to 4 dash. Now 3 to 4 dash represent an isentropic compression, which is not the case because we don't have any turbine in a vapor compression refrigeration cycle. So there's no need for turbine to expand the gas. So what we do is we just diffuse it, meaning that we just let it blow away. So in the process of letting it blow away, you will have a drop in temperature and also a drop in pressure, but without doing any work. That process is called throttling. So basically, throttling is a process where no work or even no external energy is given. So the process is basically constant enthalpy. Okay, the enthalpy doesn't change, so you also call isenthalpy process. And then finally, the refrigerant becomes liquid again, and from 4 to 1, it's a constant pressure. Heat absorption, heat is absorbed from a cool environment. So this is QL, and bear in mind T4 is smaller than the refrigerated section. So let's put this T small r for refrigeration, for the refrigerated space. Okay, so that is how the cycle is completed. Now, for our example 11 and 1, we have 3 key points. The refrigerant is 134A, which is an ammonium-based refrigerant. Is it ammonium or ammonia? NH3 is ammonia, okay, ammonia gas. Okay, it's an ammonia-based refrigerant gas, and the working pressure is from 0.14 to 0.8 megapascal, and the mass flow rate for the refrigerant is given to be 0.05 kilogram per second. Now what we need to find is the rate of heat removal from the refrigerated space, and 2, the power input into the compressor, how much energy or how much work we are getting from the compressor, and number 3, the rate of heat rejection to the environment. This is basically QH. Okay, and finally, the most important parameter is the COP for refrigeration. So let's have a look at the solution. And there again, I redraw the diagram into a simpler, more straightforward version. So you have a process from 1, 2, 3, and 4, and we are going to walk through the process state per state. So first we start at state 1. The pressure at state 1 is the lowest pressure, so it's 0.14, and the pressure at state 2 is 0.8. So the enthalpy at pressure 1, state 1, is you can get the enthalpy values from the refrigerant table, refrigerant 134A table. That is, textbooks, it's table A12. This is just a direct reading from the table. Also, we can get S1 directly from the table too. Now, at P2, at state number 2, because the compression is isentropic, so S1 equals to S2. Now we have, because of this problem, we have to figure out H2 by using interpolation. So S2 within the pressure of 0.8 megapascal MPa, so the range is somewhere between 0.9183 and 0.9480. This is from table A3 at pressure 0.8 megapascal, and the enthalpy value reads from 267.29 to 276.45. And using linear interpolation, if you walk through the maths slowly, which is something that I really wish you do, because it's going to take some practice to get good at it, you end up with H2 equals to 275.389, or as in the textbook, on the work example of the textbook, it's let me see, 275.39. So there you go, you have the enthalpy value at state 2. Next is state 3, where we have state 3 is in the constant pressure line of the process 2 to 3. So we can have P3, we can determine P3 from that to be the same as P2, which is 0.8 megapascal. And because this is a constant pressure that doesn't have any interference from pumps or turbine, so we can directly refer to our table A12 for the reading of enthalpy of the enthalpy value. So H3 is enthalpy value reading of fluid at 0.8 megapascal, so the value is 95.47 kilojoule per kilogram. So at 3, this is already in fluid form. Okay, So that's why we use the HF, fluid form. And since the process from 3 to 4 is a throttling process, the enthalpy doesn't change because it is an isenthalpic process, constant enthalpy process. So we can deduce from this information that H3 is equal to H4. So we can conclude that H4 is equals to 95.47 kilojoule per kilogram. So from there you go, you have H1, H2, and H3 and H4. So the first step is heat removal from the refrigerated space. So the refrigerated space is a process from 4 to 1. So meaning that the enthalpy difference will be the difference between enthalpy 1 and enthalpy 4. Plus, you have a mass flow rate there. The value of our reading here for H, small h, is kilojoule per kilogram. So that's why we need the kilogram values. And if you calculate the difference between H1 and H4, you will end up with the enthalpy value per kilogram. And that is why we need to multiply it with mass flow rate of 0.05. So if you do the math, you have 7.1845 kilojoule per second, which is also equals to kilowatt value. So you have the value of 7.18 kilowatt there. So that is the rate of heat removal from the refrigerated space. And as for number 2, the work done by compressor, again, it's from state 1 to state 2. The process is isentropic. So you just take the difference between H2 and H1 and multiply by the mass flow rate, and you get 1.8115 kilojoule per second, or 1.81 kilowatt. And the heat rejected to the environment is the difference between the process state 2 to 3. So there you have H2 minus H3. Yeah, H2 minus H3. And if you do the math, you have 8.996 kilojoule per second, which is about 9 kilowatts. And finally, the COP for the refrigeration is the heat rejected from the low temperature, which is 7.18 kilowatt, divided by the work done by our compressor, which is 1.81 kilowatt, and you have 3.97. This is remember, this is a non-dimensional parameters. And of course, the higher the better. So let's put a conclusion there. The higher COP, the better. So that's it for our work example on the ideal vapor compression refrigeration cycle. We will work on other example this Friday, as usual in our classroom, and I see you in Friday.